Assalamu alaikum. Welcome to the next class. So we'll continue from the previous class, and we're discussing about the influence of the SVC on the system voltage. How system voltage will be changed when we change the susceptance or when we change the current taken by the SVC. That depends upon the susceptance of the SVC, and finally it depends upon the current that is taken by the SVC. So as shown in the figure below, the representation of SVC. In the earlier class we have done the same thing, but we did not consider the coupling transformer. Here we are taking consideration from the transformer as well. We are representing the transformer by a reactance, leakage reactance of XT, and when we connect the high voltage bus and SVC bus through the transformer, so we can represent it by a simple leakage reactance. The high voltage side VH, and then is then related to the low voltage side VSVC as. So you can see this from this point, this is VH and SVC. You'll see it becomes a voltage divider circuit, where this VH will be divided between XT and you can say VSVC. So this voltage will be equal to, VSVC in terms of VH will be equal to reactance of this divided by reactance of this plus reactance of this. That will be equal to let's say it is XL divided by XT plus XL. So I will divide it by numerator multiplied by, of course, VH. I will divide the reactance part by XL on numerator side as well as on denominator side. So it will be equal to 1 divided by 1 plus XT divided by XL, where 1 by XL can be taken as VSVC susceptance of this. That is what this is. So VSVC is equal to VH divided by 1 plus XT into BSVC, or VSVC divided by VH is equal to 1 divided by 1 plus XT BSVC. You can also derive it on your own. This is very simple. You can use the voltage divider rule to derive this. Now you can cross multiply it. It will be VSVC into 1 plus XT BSVC is equal to VH. When you do this, after that we will linearize the above equation, or we will differentiate it, and then will not limiting its value to very small value. We'll keep it as it is, delta. So delta VSVC, since delta VSVC and this VSVC both are changing because they are the function of each other. So we can say delta VSVC is equal into 1 plus XT BSVC naught. That means this will be the value of this. When we change this, we are keeping this BSVC constant at that value. When we take this as a constant, we can say that value will be equal to BSVC naught. Now, well, we are keeping this constant, that's VSVC naught, and we are differentiating this term. This will be 0. This will be equal to delta XT into delta BSVC. That is equal to delta VH. We have to actually find out the variation of this VH due to variation of delta VSVC. So we have already done this for the SVC without coupling transformer. Now we'll see how the coupling transformer makes its presence used. Now substituting the equation 5, this is equation 5. Substituting the equation 5 and the expression VSVC naught divided by VH naught from equation 4, that is this will be the constant values because we're not considering them to be changing here. So in equation 3 we get this equation. So this is 5, this is 4. We have to substitute them in equation 3. We have actually derived this equation. This is the final result of the change in SVC voltage with respect to the BSVC. In the earlier class, I have written that equation over here. This is the equation 3 in the previous classes. So it will be equal to delta VSVC divided by delta BSVC. That is equal to minus VSVC naught ESCR plus BSVC. So we have to put the values of these quantities from equation 4 and equation 5. So final result will be this. This will be the change of the high voltage bus with respect to the change of the BSVC. That will be this equation. So this is how you can see the difference. The voltage of the system, because high voltage on this bus, that's high voltage, actually the system voltage, can be changed by changing the susceptance of the SVC. Now we'll come to the application part of the SVC. This was about the change in the different parts or different components of the SVC on the system voltage. Now we'll see the application. The first application will definitely be the voltage control or reactive power control that we were discussing until now. So this can be used for the load compensation as well. Because sometimes if we I have not discussed the load compensation in the class. So load compensation means we are actually compensating the reactive power at the load side, so that we can use them on the load side to have different types of compensations. So that's what load compensation means. So in high power network, SVC are used for voltage control that we have discussed, and for the attaining several other objects such as damping and stability control. So actually we will now discuss about the stability control. We will not discuss about the damping control. We'll only discuss about the stability control, because you already know, you already have this study the stability in detail in power system second course. Although until now we have discussed the voltage control extensively, so the application of SVC as stability enhancement will be discussed now. Now, before going into the actual discussion about the transient and steady state stability, I will first discuss some things, some topics which will finally lead us to the discussing about the improvement of the steady state transfer capability of the system. First, let us say we have a system, we have a two machine model, or we have a single machine infinite bus model. So in that case, the P delta curve for an uncompensated system will be given as V1 V2 by X sine of delta, where V1 is the voltage at this sending end, V2 is the voltage at receiving end, X is the impedance between these two, and sine delta is the angle between this voltage and this voltage. So the curve when we draw for this, that is PWC with respect to this delta, it will be this curve. Similarly, the other transmission system where we have assumed, here we have assumed the shunt capacitance to be 0. Here we'll be assuming some distributed shunt capacitance. When that is the case, our expression will be modified like this to be identical in the numerator, and the sine delta will be identical. Only X will be replaced sine Z0 sine of beta A. This will be in general for a long transmission line where we cannot neglect the capacitance. So in that case, as we have discussed in the previous class, that this Z0 sine of beta A for long transmission line will be less than this X, so that this portion, overall this portion, will be greater than this. So when this is the case, we can say this is the system, and this capacitance is considered, this will be the P delta curve. It will definitely be different in the peak, but the variation will be similar. You can see from here, this will be PWC. This will help us in understanding about the steady state power transfer capacity. That is why I discussed it over here. Second thing is that, let us say we have a capacitor in between the line where it is dividing the line in two parts, X by 2 and X by 2, and this is V1 and this is V2. For uncompensated system where we don't have a capacitance in between the line, we have only this reactance and this reactance, the power transfer between these two will be governed by this equation. That is P is equal to V1 V2 by X sine of delta. This is the uncompensated system. Let us say we use a capacitor for compensation in between the line, a fixed capacitor whose reactance is given by minus JXC. So this will be our system. It will look like. Now we'll try to find out how the power transfer capability will be modified. We'll convert this. This will be a T system, a T model. We can convert it to a pi model, or this is actually a star system. We can convert into a delta system. So in that case, delta will be formed like this. So from here, delta will be formed like this. This will be Z dash. This will be, let us say, any other impedance, Z1 or Z2. Here we are only interested to find out the Z dash, because when we find out the power, the final circuit will be like this. When we convert it into delta, it will be like this, because this point is actually a ground point. You can connect it here or here or here. That is one and the same thing. So the power transfer from this to this by changing this system to the delta system it will be equal to v1 v2 by z dash sine of delta, because power transfer will not depend upon these two things. It will only depend upon the impedance that comes between v1 and v2. Now we'll find out the value of z dash. So z dash will be found from this circuit by using the star delta transformation. Here we have to transform this star into delta, and we know that when star is transformed into delta, we have first the numerator will have uh, the multiplication of impedance taken two at a time of all, let us say this multiplied by this plus this multiplied with this plus this multiplied with this, divided by the impedance that we are calculating, divided by will be the impedance which is opposite to that impedance which we are calculating. That means the first z dash will be multiplication of these two, that is minus, sorry, j into j will be equal to j square, that's minus 1, x square by 4, that is this, minus x square by 4. Then this multiplied with this is minus j into j, that will be equal to minus j square, that will be equal to plus 1, it will be equal to xc into x by 2, that is xc, x into xc by 2. Similarly for this case, minus j into j, that will be equal to 1, x by 2 into xc, that is xc into x by 2, that will be like this. When you add these two, it will be equal to x into xc, and then finally when you divide this jxc to this minus and minus will cancel out. When you take j to the numerator, it will be equal to minus j x square by 4xc, that is here minus j x square by 4xc. When you take this minus j to the numerator, it will be plus j into xc into x, xc into x. When you divide it by x, xc and xc will cancel out, it will come out to be only x. So total reactance of this system will be now that z dash will be equal to j into x minus x square by 4xc. You can see from this relation, and when you compare this relation and this relation, this will be definitely less than x. When it is definitely less than x, you will see that this portion will be greater than this portion. So when you draw the p delta curve for this system, it will be equal to like this. This will be compensated system, or we can see when you use the capacitor as a compensator at the middle of the line. This is an uncompensated system, that is this equation. So here also you can see this will be its graph. It will be exactly above this graph. The variation will be same, that is the initial value and the final value will be at the same point, but other points will be always greater than for this system. So this is how this compensated system will change the maximum power transfer. Now the maximum power transfer will be given by this equation v1 v2 divided by z dash is equal to x minus square by 4x. So keeping these things in mind, we'll now do similar things which actually we have already derived and discussed in the first two or three classes, but I would like to go or revive them again, because I need them to explain them stability. Let us consider this single bus infinite bus system interconnected by a tie line, which is a lossless line. So the power transfer capability between these two will be given by this. This is the well-known equation that we have been using quite significantly. That's v1 v2 by x sine of delta. For these two voltage to be same, it will be equal to v square by delta. So this power will vary as a sinusoidal function of the angular difference, that is this delta, at the synchronous machine and the infinite bus. So the maximum steady state power that can be transferred will be at delta is equal to 90 degrees. That will be equal to P max, that is v square by x. This will be used when we have this will be the value of the P max when we are using an uncompensated line. When we use the compensated line, that is when we use a compensation at the middle of the line, and we are using an ideal compensator whose reactive power rating is infinite. That's whatever be the active power transferred from the receiving end, sending end to receiving end, the reactive power that is supplied by the capability of the compensator to supply the reactive power will always be there, and it will always keep this midpoint voltage constant irrespective of the real power drawn. The SVC bus voltage at the is then given by Vm at an angle of delta by 2. This is Vm at an angle of delta by 2, and it will again be equal to, let us say, this voltage and this voltage. So the power transfer from this to this will be now enhanced like this. It will be equal to V1 V2 divided by x by 2, that's half of x, into sine of delta by 2. This equation also we have derived already, but you need to understand this figure. Now the power transfer equation at this, that will be equal to, when V1 is equal to V2 is equal to, will be equal to twice V square by x sine of delta by 2. Here the P max will be now increased to twice V square by x. So by using xc, that is the capacitor only that has increased the power transfer capability, but not exactly. That depends upon the value of xc. What's the value of xc? So we can make it to 2 times twice Pmax, sorry, twice Pmax or higher than this. But here it will be exactly equal to twice Pmax. So the maximum power occurs, that is delta by 2 is equal to 90 degrees, that is delta is equal to 180 degrees. Now here is one important point. In other words, the midpoint ideal located ideal SVC doubles the steady state power limit and increases the stable angular difference. That is very important. Stable angular difference between the synchronous machine and infinite bus from 90 degrees to 180 degrees. That means earlier you can see for an uncompensated system, the system was stable for the slow changes uh, in the power. It was stable from 0 to 90 degrees, and it was unstable from here to here, because you can see when mechanical power increases, so electrical power is not there to compensate that power. It will then decrease for increasing the rotor angle. But when compensation is done, you can see the power angle will always be increasing. The instability problem will always be, for this case, will be eliminated. That is what it is meant. Similarly, if the transmission line is divided into n equal sections with an ideal SVC at each junction of this section maintaining a constant voltage magnitude V, then the power transfer at speed dash C of this line can be expressed as. So theoretically it will be equal to P dash C, it will be equal to V square by X by N sine of delta by N, and the maximum power that can be transmitted along the line will be N into V square by X. In other words, with n sections, the power transfer can be increased n times that of the uncompensated line. That seems okay, and that seems to be quite tactical. By increasing the different types of compensators at making n equal sections of the transmission line, the voltage profile may be constant throughout the line or very close to the constant throughout the line. But the theoretical limit, it may be understood it is only the theoretical limit. The actual maximum power flow is restricted by the thermal limit of the transmission line. That means when we increase the power transfer, power is transferred actually through the transmission line, it results in the flow of the current, more flow of the current through the transmission line. When current flows, due to the inherent presence of the this conductor resistance, there will be the heat loss or through the resistance, which results in the heating of the transmission line. And when we increase the power transfer, it may also increase the heat loss, which may result in the melting of the or burning of the transmission. That is what is meant by the thermal limit. And that thermal limit, we can say that for every transmission line there is a limit of the current beyond which this thermal limit can be it can reach. So keeping this in mind, thermal limit, we cannot go beyond that limit. Having, we can increase the n up to infinity, we can have compensators at every interval of the transmission line, and we can increase the power transfer. That will be definitely determined by the thermal limit. Now, one more important thing that you need to understand, that this ideal compensator, when we use it at the middle of the transmission line, its reactive power should be equal to 4V square by X or minus cos of delta by 2. This also we have derived in the first classes. So its maximum reactive power will be equal to delta is equal to 180, that is the 4 times Pmax. So that has to be kept in mind. So that means to increase the real power to twice Pmax by the compensator, it has to supply as much as 4 times Pmax the reactive power. So such a high rated SVC is not economically feasible. So what will happen, and what are the practical limitations of this, we will see now. That until now we are assuming only the ideal case of the compensators. Now the power transfer increase achievable with realistic SVC of limited ratings is depicted in the form. Now we will see the actual whose ratings are limited by some design constraints, and we know that practically there will not be any compensator which can give us the infinite amount of the reactive power. Now curve A here shows the uncompensated system. We'll assume the same system. This system, we have single machine infinite bus system, and we are using an SVC at the middle of the line, or we can say compensator at the middle of the line. But this compensator is now is not an ideal one. It is a non-ideal or practical, which has some reactive power limit. In this case, we assume that its reactive power limit will be twice Pmax. Now for uncompensated system, this will be the curve that is we have to be governed by the equation P is equal to V square by X sine of delta. Curve B shows the same relationship for an ideal SVC for a large reactive power rating. SVC is a 4. That is, curve B will be like this. This is the relationship of the real power. It will be equal to twice V square by X sine of delta by 2. So curve B is not only this much, which is written here on the bold line. Curve B is from 0 to this line, which we have already. The maximum will be given by twice Pmax. Okay, and this curve B is also we have to take care of the reactive power. Reactive power, and this curve B is actually this curve in the other figure. So in this case, we are assuming that the reactive power supplied by the SVC is 4 times Pmax when real power is twice Pmax. Okay. Now, curve C represents the power angle curve for the middle line located fixed capacitor. This is the curve C, or we can say this is the curve which we have already derived for a capacitor at the middle of the line. You can see this is the curve for the uncompensated system. This is the curve for a fixed capacitor at the middle of the line. This is this. So you understood this. I have drawn this curve again for this circuit. This is the curve C for the fixed capacitor at the middle of the line. Now, this curve is based on the corresponding equivalence reactance between the synchronous generator and the infinite bus. All these curves actually are drawn by taking care of the equivalent impedance between the infinite bus and transmission line. We have also already derived this curve when we place a capacitor at the middle of the line, and we finally calculate the value of simple impedance between that synchronous generator, or we can say synchronous machine, and the infinite bus. That was actually Z dash. So all these curves are drawn by calculating that impedance. If an SVC is incorporated of a limited rating compensator, let us say that is only twice Pmax. That means we have an SVC whose reactive power capacity is only twice Pmax. That means if we increase the power, real power, from this point to this point, the reactive power also increase like this. At this point, when the rating of this SVC reach twice Pmax, it will be able to compensate. It will be able to give this much of the real power. That means this. After this, since we know that it ensures the voltage regulation until its capacitive output reaches its limit. Now, that limit is this point. When it reaches at this point, the real power is drawn. The real power by the system is drawn by this much. That is, it is not by 2 max. It is slightly less than depending upon this point and this point. Okay. Now, above this point, since this is the maximum rating of the reactive power, this SVC will act as a capacitor, fixed capacitor. So why does this happen? Because usually you might be confused about why will act it as a capacitor, why not an inductor? Because for most of the cases, you will see for almost all the cases, we are transmitting the power which is greater than the surge impedance loading. When that is the case, you will see that the voltage curve, the voltage and distance curve will be below the surge impedance, or we can say flat voltage profile curve. When that is the case, that means this TCR, or we can say SVC, has to work in the capacitive mode. When this is the case, when voltage goes on decreasing, the capacitive current drawn by the SVC has to increase. So when it goes further and it reaches the limit, that will, after that, it will act as a fixed capacitor. So that is why it will only discuss this fixed capacitor arrangement of this SVC, because practically it will be mostly used in the capacitor range. Now, after its limited range in the capacitor range, it will act as a fixed capacitor. So this curve D, that is of this figure, that's curve D is this one. Curve D represents the power angle curve that shows this fixed capacitor behavior and demonstrates that the realistic power limit transfer will be much lower than the theoretical limit of 2 Pmax if SVC has a limited rated power limit. If this is the case, after this point, that is at this point, it will follow this curve up to 2 max. Up to 2 max, you will see the real power will follow this curve up to this point. And after this point, since it is acting as a fixed capacitor, it will follow the fixed capacitor line, that is this. This is the real power, you can say real power and delta curve for the realistic, or we can say practical SVC, not this one. This is the curve for the ideal SVC. So for practical SVC, it will follow the ideal curve up to the rating of the SVC, that is the limited rating of the SVC. When the limited reached, it will act as a fixed capacitor. It will follow the capacitor curve, that is this. So this will be the final curve of the practical SVC. From here you can see there are still advantages. You cannot see that these advantages can be eliminated having some fixed rating or limited rating. You can see the peak of this has increased. Definitely it is not equal to 2 Pmax, but it is still greater than this value. And in ideal case, we have actually eliminated the instability problem. The instability problem that was from 90 to 180 degree has now decreased. It will be definitely from this point to this point. This point will depend upon the rating of this and the capacitor fixed value of this, that is this. Definitely it will be less than this range, that is 90 to 80 degree. Let us say it will be 120 to 180 degree will be the instability range of the power system. We can say from this to this, steady state stability has increased. You can see from here, that is one point. The second point, since peak has increased more than Pmax, we can say steady state stability has also increased in that way as well. So coming to this, therefore the ideal or practical transform compensator, since the peak of the P delta curve increased, the steady state stability will increase. This is one important point. As far as ideal compensator is concerned, there would have been no stability problem if compensator has infinite power capacity. We have discussed it because for that case, from this point to this point, you will see electrical power is always increasing. When we increase the this mechanical power, electrical power will increase, that rotor angle increases. So it will there will be some point when they we can say they equalize each other and there will be a stable equilibrium point. But here, for this case and for this case, you will see there will be instability for increasing rotor angle. If PM increases, rotor angle increases, but electrical power decreases. There will be a difference between the mechanical power and electrical power that goes on increasing and results in the instability. But one thing is that when peak increases, stability will increase. There is also a range from 90 degree to this point. You can see that stability margin has increased in steady state stability. Because in earlier case, we say that the stability in the stable range for the synchronous machine or the system power system is from 0 to 90 degree, but here this range increases from 0 to, let us say this let's say 130, 140, 150. It depends upon the rating of this compensator. It has increased, but it will be definitely less than this twice speed. So this is about the steady state stability. Now let us come to the transient stability. Now this is the case when we have the uncompensated system. We assume that the system is operating at this point, and at this point a fault occurs. When fault occurs, suddenly the electrical power will go to 0. You will see that the Pmax and the area that is under this curve will be resulting at the accelerating area. Now the fault is cleared at delta 2. When delta 2 fault is cleared, you will see that the electrical power has reached to this point. Because from this point to this point, since there is no electrical power, there will be accelerating power and rotor angle will increase. Rotor angle will increase. That is why it goes from delta 1 to delta 2, and when fault is increased, electrical power is restored to this point, and when this is restored to this point, there will be some deceleration, and deceleration will be there, but rotor angle is still increasing, but with decreased speed is decreasing. So I have discussed these things in the previous classes. So until this, let us say until this point is go on, until this area 1 is equal to area 2, this delta will go on increasing up to that point. Let us say that point is delta 3. So from delta 3 there will be some oscillation, and finally it will settle down again at delta 1. So there will be some area which will be, let us say, remain there for the system to be stable. It means that if we increase, if the fault has been increased at slightly greater than this, this area 1 would have been then equal to the whole area, and we can say that delta 2 dash would have been the critical clearing angle. So we can say critical clearing angle, or the time to which it will be fault should be cleared, is less as from this delta 1. But for this case, you can see this area 1, since the area has increased in this case, you will see that the area under the curve from this point to this point will be equal to this only at this point, because now area has increased. This delta C3 will be less than this delta 3. So the remaining area for this rotor angle to sweep is very large. That means margin of stability, transient stability, has increased. And in previous classes, that is in power system 2, I have discussed in detail about when area increases, this transient stability increase. It is because of this area, that is available area for the system to sweep the voltage, to sweep the rotor angle, is large. So when this is the case, you can see here, since area is large, the area available for the rotor angle to sweep is large, transient stability has enhanced. So this is also one you can say another advantage of using SVC. Steady state stability has increased, transient stability has also increased. Now let us try to do some numericals. It will help to understand how to approach different types of the problems. We have a single phase uncompensated system with VS, VR is equal to V is equal to 132 kV, X is equal to 32 ohm, delivering a real power of 100 megawatt. The value of delta and line current will be, we need to find out the value of delta and line current. This is actually, let's say, a two machine system who are connected through an axis 32 ohms. The exchange of real power is 100 megawatt. We know that the power transfer is given by this equation, V square by X sine of delta, that is 132 square divided by 32 sine of delta is equal to 100. Delta will be equal to 10.58. So the equation of I, which we have derived from the triangle, that actually relates this the voltage drop, VSVR, and the voltage drop. So from that relation we can get this is equal to twice V by X sine of delta by 2. So 2 into V divided by X sine of delta by 2, it comes out to be 760 amperes. Now for the same system, we are using a series compensation where K is equal to 0.2, that is series compensation factor is 0.2. We need again to find out the value of this delta and this I. So we know that when series compensation is done, it will be equal to V square by X into 1 minus K sine of delta is equal to 100. For same power transfer, we need to find out the value of delta and I. So 1 minus K, 1 minus 0.2 is equal to 0.8, that will be equal to 0.8. So delta will be equal to 8.44 degrees. So I will be equal to twice V divided by X 1 minus K sine of delta by 2. It comes out to be again almost same value of the delta. Even for the same current, because here delta has reduced, this has increased, this whole term has increased, or we can say this has reduced and this has reduced, the reduction of this and this will cancel out each other. So in that case, this current will be 758. Now earlier this was the uncompensated system, it was operated at this point, this would have been delta. Now it is the compensated system. For the same power, it will operate at this point. Of course, this is not actually the exact same labeling is not done, identical labeling may be different, but I just want to note that earlier it was operating at this delta, now delta will reduce, delta will be 8.44 degrees for the same power transfer. Now next example, for a TCR, find the value of sigma if alpha is equal to 100 degrees. So you need to be very careful about this. Here it is not given whether the alpha is with respect to origin or with respect to peak. Since alpha is given as 100 degrees, and we know that if it has been given with respect to peak, there the alpha ranges from 0 to 90 degrees. Since it is given that alpha is equal to 100 degrees, it means it is given with respect to the origin. That means with respect to peak, alpha will be equal to 10 degrees. So sigma is equal to pi minus 2 alpha, that is equal to 180 minus 2 into 10, that is 160 degrees. Now, for alpha is equal to 10 degrees, find the value of BTCR if BL is equal to 0.16 Siemens. So BTCR alpha is equal to B max 1 minus twice alpha by pi minus 1 by alpha sine of 2. But you have to be very careful here by using this equation. Here alpha should be in radians. Here you can use alpha in radians or in degrees, that is material, but here it should always be in radians. So by calculating the value of this, putting the value of alpha is equal to this 10 degree here in radians, or here you have to be careful in one direction, that if you use here also alpha in radians, you have to change the mode of the calculator in the radians. If you use here directly sine of 20, that's 2 into alpha is 20, so you have to use the this calculator in degree mode. That you have to take care. So this is the value of BTCR. So that is 0.12487. For the above system, find the reactive power consumed by the TCR for a voltage of 33 kV. So we need to find out the reactive power consumed. That is simply this Q will be equal to V square BTCR. V square is this, BTCR is this. This is the maximum value of the reactive power consumed by the BTCR. Now one more example. A single phase system has a sending end voltage of 132 kV and receiving end voltage of 138 kV at no load. Find the value of inductive reactance and the corresponding value of firing angle of the TCR to make the receiving end voltage equal to 132 kV. Okay. Also locate the operating point on the VI characteristics of the SVC along the VI characteristics of the transmission line. Assume X is equal to 100 ohm and BL is equal to 0.1S. So Q is equal to, as we know from the transmission line point of view, Q is equal to VR by X into VS minus VR. So VR is 132 divided by 10. This is equal to 138 minus 132, and the calculate is 79.2 MVAR. So that means this much of reactive power has to be consumed by the TCR. So that means Q, that is V square BTCR, should be equal to this much. That means Q, this BTCR should be equal to Q divided by this V square. That's Q is this, V square is 132, because here it is MVAR, this is 10 to the power 6, 132 K square will be again 10 to the power 6, that will cancel out. We can use that like this. So BTCR is equal to 0.00455 Siemens. So since BL is equal to 0.1 Siemens, so it means 0.00455 is equal to 0.1 into 1 minus twice alpha by pi minus 1 by alpha sine of 2 alpha. So by solving this equation, this is a nonlinear equation, you have to solve it as I have told you in the power system, that you have to solve it by using the calculator directly. You just write the equation on the calculator directly like this, and then keep the mode of the calculator in radian mode, and then give the value of initial value of alpha between 0 to 90. Let us keep it as pi by 4. In that case, you will get 1.088 radians. So the final alpha will be 62.35 radians. One more thing that I need to have, we have to actually calculate wait a minute, because okay, now here we have to locate the operating point on the VI character. This is the VI characteristics. So here alpha is equal to 62.35 degrees. Since we know that this is alpha is equal to 0, this is alpha is equal to 90 degrees. So here you can say equal intervals are made. This is 30 degree, this is 60 degree, this is 90. That means operating point will be roughly over here at this point. So you need to be very careful about calculating or about identifying the operating point. For this case, that means calculating this alpha on the calculator, I will show you another video. I will put the link of that video in the description of this video. You can check that. Actually, I have shown in the power system first perhaps and power system second as well. Okay, I will today I will stop over here. This will be enough for today. Thank you.